Okay, so camera option. Whoops, didn't mean to do that for those of you guys here. There we go. So we have two equations, y equals 3 to the x and y equals 1/3 to the x. We know that exponentials take this form, a times b to the x. Okay, b, the base, or the b right here, is the value that tells you how the exponential is changing. If b is greater than 1, you're going to have an increasing exponential function, which shows growth. If b is less than 1, specifically between 0 and 1, because we're never going to have any negatives there, then you're going to see a decreasing graph that shows exponential decay. So the opposite of something growing is something decaying. So you're either going to see growth, which is increasing, or decay, which is decreasing. The value a in the front is the y-intercept. So right here, this value is the y-intercept. It occurs when x is 0, because if you put a 0 in for x, b to the 0, b to anything to the 0 power is 1. So when you put b to the 0, this whole thing goes away, which is why you end up with a as your y-intercept. Some people call that the starting value because it's what happens when x is 0. And then b again is the growth factor. So I'll call it the growth / decay factor, because of course, if it is less than 1, you're actually seeing decay and not growth. So those are the two values that are in our equation. So our first one right here, y equals 3 to the x, okay? Notice there is no number in the front. So right there in front of the parentheses, there's nothing there. But there is always something there. If you can't see it, it's a 1, because 1 is the only number that you can multiply by something that you don't have to write it in. 1 times something is itself, so there's no advantage in writing a 1 in there as a 1 times something. Okay, so 1 times 3 to the x tells me, oh, my a value is going to be 1, and my b value is going to be 3. So to graph this, I can, if I want, set up a table and then just plot points. I can also just use the a and the b and go straight to graphing this. Now, if a is 1, that's my y-intercept. So I know that I can put a point at 1, 0, 1. That's my y-intercept. Okay. My growth is 3, and it's growing because this number is greater than 1. So I'm going to see a growing, increasing exponential. A factor of 3 means I am going to go to this number here, 1, and I'm going to multiply it by 3. So my next y value is 1 times 3 is 3. 1, 2, 3. So I move over to my next x, and my next y is 3. So right there, this one's at 1, this one's at 3. Okay, now I'm going to multiply by 3 again. That's going to give me 9. So my next x value, or y value, I should say, sorry, when I put in my x is going to be 9. So I've got x is 0, and then 1, and then 2. And what happens to my y's? I've got 1, 3, 9. They're tripling. My next y would be 27, and I definitely don't have room for 27 on this graph, so I'm not going to go any further to the right. I can also move backwards. If this is 1, instead of multiplying by 3, I can divide by 3 or multiply by 1/3. So if I take 1 and divide that by 3, I get 1/3. So this y value is going to be at about 1/3. And then I divide by 3 again. I'm going to be at 1/9, which is very close to the x-axis. And then divide by 3 again, 1/27, which is even closer to the x-axis. And then 1/81, which is super close and super close. So all that's happening here is we're just getting super, super, super close to the x-axis. But remember that we never actually reach the x-axis because the x-axis is what we call an asymptote. So I got an arrow here, an arrow there, and this one is y equals 3 to the x. Okay, so there's the graph of y equals 3 to the x. Okay, the other equation, y equals 1/3 to the x, the a is still 1, and the b value is now 1/3. So this value is less than 1, so this is going to be a decreasing graph, or it's going to show exponential decay. So this graph is going to show decay. However, still going to start with the same y-intercept at 1. So I can still start right here at 1. In other words, both of the graphs are going to share that point right there. Okay. Now, as I move to the right, I'm decaying, I'm decreasing. I'm multiplying by 1/3. So 1 times 1/3 is 1/3. And then 1/3 of that is 1/9, and then 1/27th, and 1/81th, etc. Same values I mentioned on this side. So we end up with the same values, just they're on this side instead of that side. Which means that if I work backwards, dividing by 1/3 is the same as multiplying by 3. So when my b is 1/3, when I go to the right, I take 1/3. When I go to the left, I multiply by 3. I triple it because that's the reciprocal of 1/3. Dividing by a fraction is the same as taking the reciprocal, multiplying by the reciprocal. So here I am at 1, and I'm going to multiply by 3, and that's going to put me at 3. And then I'm going to multiply that by 3, which is going to put me at 9. And hopefully you can see that the blue graph here is a mirror image. It's a reflection of the pink one. And this one is y equals 1/3 to the x. Oops, to the x. Not going to let me write an x, is it? There we go. Okay, so our two graphs are very similar. In fact, the only difference between them is that one is increasing and one is decreasing. They're doing that at the same rate. So increasing by a factor of 3 is the exact same speed or rate as decreasing by a factor of 1/3. So in other words, the reciprocals actually show the same rate, just one is increasing and one is decreasing. And the two graphs are basically mirror images of each other. Okay. Now, what are the x and y intercepts in the domain and range for each equation? Now, they're actually the same. Both of these equations have the same x-intercepts, y-intercepts, domain, and range. So I don't have to write it out separately for each one because they are the same for both. So the first question, x-intercepts. So looking at my graphs, where do these graphs cross the x-axis? Here's the x-axis down here. So where do these graphs cross the x-axis? It is kind of a trick question. So where are our x-intercepts? Okay. How about, do these graphs cross the x-axis? No, there are no x-intercepts. X-intercepts means you actually have to hit the x-axis and cross it. So both of these graphs, the x-intercepts, there are none. In other words, they're never going to cross the x-axis. Reason there are none is because instead of an x-intercept, they have an asymptote. Strange word, asymptote. But an asymptote is there a horizontal line? Sometimes there's vertical lines, but not this year. In other more advanced classes, you'll see graphs with vertical asymptotes. But in our case, is there a horizontal line, like that one, that the graph gets closer and closer to and never crosses? And yes, it's the x-axis. It's the line y equals 0. In other words, what's happening to the y values here? They're decreasing and getting closer to 0, but they never hit 0. So they never hit the x-axis, which means there are no x-intercepts. Okay? An x-intercept occurs when y equals 0. But there is no y equals 0 because it's an asymptote. An asymptote is a value that you get closer and closer to, but never actually reach. Okay, our y-intercepts for each graph. Okay, we can see both of them hit the y-axis at 1. So they both have the same y-intercept of 0, 1, and that's because they both had an a value of 1. So remember, the a value is the y-coordinate of the y-intercept. So the a tells you where the y-intercept is. So they both have the same y-intercept. Okay, now we got to go back to, I think this was like end of August, beginning of September. Domain and range. Okay, domain is the values of x on a graph going from left to right. So if we take a look at this pink graph right here, to the left, notice there's an arrow. As I go to the right, there's another arrow. This arrow is headed to the right. It's going up, but it's also going to the right. So to the left, there's an arrow. To the right, there's an arrow. That means every value of x is on this pink graph. Same thing on the blue one. We are going to the left. There's an arrow, and to the right. Hello. Yeah. Yeah. Roshan is not here today. Okay. But everybody else is. Okay. So anyway, that puts our domain as you go forever to the left and forever to the right. That makes our domain, remember we called this back in our functions chapter, all real numbers. If you don't want to write all real numbers, you can say from negative infinity to positive infinity, or you can use the all real numbers symbol, which is that fancy little R with the 2 lines on it. Okay, range. Okay, so domain is the x's that go from left to right. The range are the y's that go from the bottom to the top. So top, if you look at both of these, they have arrows. So that means both of the ranges are going to go forever up towards infinity. But if you look at the bottom of both graphs right here, this is as low as they go. They don't go into the negative region at all. In fact, they don't even hit 0 because of the asymptote. So our range is that y's are just values greater than 0. And hopefully they're all coming back real soon. So our range is all values of y that are greater than 0. Now, all of this information that's here up on the screen is true for every exponential that we do. I'm trying to get rid of that glare. There we go. So every exponential that we are going to do in this course, all of this applies, with the one exception that the y-intercept can change. So the y-intercept will change depending on the value of a, but other than that, everything here will always apply. In other words, every exponential will have no x-intercepts. Instead, it will have an asymptote at y equals 0. Every exponential we look at will have a y-intercept based on the value of a. So that value will change, but every exponential will have one y-intercept based on that value of a. All exponentials will have a domain of all real numbers. That means they go forever to the right, forever to the left, all real numbers. Every exponential will have a range of values of y that are greater than 0. So if you are asked what any of this is for any exponential, it's this. It will not change. The only value that changes here is the a. So whatever your a is, you can answer all of this. Doesn't matter what A is, you're going to say there's no x-intercepts. There's an asymptote at y equals 0. My y-intercept is 0, comma, whatever A is. My domain is all real numbers. My range is y values greater than 0. So everything here applies to every exponential that we are going to do. So hint, you might want to know that. So you might want to know what the domain and the range is for every exponential. All real numbers for the domain, range, values of y that are greater than 0. All exponentials have no x-intercepts, but they do have an asymptote at y equals 0. All exponentials have one y-intercept that is determined by the value a in the equation. Okay, so what we're going to work on today is I've got a pair deck that I'm going to put on the screen, and I'll put the link in the chat for those of you guys that are here in Zoom. But what we are going to do is look at some exponential situations. So I'm going to grab this link. And I'm going to put that in the chat. And yeah, Bertrand, I know you are here. There's just someone from the office came, but you're not, physically here. So that's what I meant when I said you weren't here. You weren't here in the classroom, but you are here. Okay, so our pair deck. Is taking its time to go to the screen. There we go. Okay, so those of you guys in class, you are going to go to joinpd.com and you're going to type in that code right there. So that code, it says underwhelmed carrots warmly officiate troubling turnips. They always have a little saying for the letters in the code. Those of you guys online, just click on the link. So those of you guys online can get to our pair deck much easier because all you got to do is click on that link. And we should see right here, tells me how many of you guys are connected. And I am finding my cursor. There it is. Okay. And let's see. In class here, we have 1, 2, 3, 4, 5. Okay, if you're just joining us, we are going to Pair Deck, which is joinpd.com. PD stands for Pair Deck. And the code is on the screen for those of you guys in the class. For those of you guys online, just click on the link in the chat. And it will take you to the same Pair Deck presentation. Okay, looks like there's 20 of you guys in. Okay, how many we got? 22. Couple more people still. Okay, so our notes for today, it's not really notes, but we're going to be going through this pair deck, which has got several different slides involving different situations that are exponential in nature. So it's a situation, a word problem, where something is growing in an exponential or decaying, growing or decaying in an exponential manner. So what we're trying to figure out from each situation is what is the value of A, the y-intercept, and what is the value of B, which is the factor that explains the growth or the decay. Okay, so I am going to close that. And that's the first screen that you guys should all see. So it says, Arnold dropped a ball during the bouncing ball activity and recorded its height in a table. Part of the table is shown at right. What is the rebound ratio of his ball? And from what height did he drop the ball? Write an equation that represents his data. Now, we've done bouncing balls before. We treated them as geometric sequences, and an exponential is just a geometric sequence. So we're going to do this the same way that we did in chapter 4 with sequences, but we're just going to use our exponential function equation instead, and it's going to work the exact same way. So as a reminder, what we're looking for is y equals a times b to the x, okay? If you are typing in Pear Deck and you want to get an exponent, remember that you can use the caret key as an exponent. For example, if you were to type in 3 caret 2, everybody would know that that's 3 squared. So anytime you want to write an exponent and you're typing, that's the key that you use to indicate that you have an exponent. It's the shift on your number 6 on your keyboard. Okay? So our bouncing ball, we've got the number of bounces over here, and we've got the height of the ball measured in centimeters. This is basically our x, and this is our y. So instead of a geometric sequence, we are going to model this situation with an exponential function. So we've got 0, 1, 2, 3, and 4. Second bounce, the ball goes up to 84.5. Third bounce, 67.6. Fourth bounce, 54.1. Okay, 2 things we need to figure out. We need to figure out how fast the ball is decaying. In other words, notice that the heights are decreasing. So the height of the ball is decreasing each time. We got to figure out by what factor. That's called the rebound ratio. It's called the B value in this equation. And then we also need to figure out the y-intercept. The y-intercept is always when x is 0. So the y-intercept is going to be this value in the table that's missing right here. So we're going to have to figure out that value in the table. And that will represent the drop height, because when the ball is dropped, it has done 0 bounces. So x is the number of bounces. This is the height after its first bounce, after its second bounce. But when the ball is dropped, it has bounced 0 times. So that value up there is A. It's also the drop height. It's also the y-intercept on the graph, okay? So there's that for the first one. So I'm going to give you guys a little bit of time to figure that out. Probably going to want a calculator. You can use one on your device, or handheld one obviously is fine as well. But you need to figure out the value A, which is that missing box at the table, and the value B. I'm pretty sure you got to find B first though. You can use B to find A. Okay. Okay, good. I see some good writing happening. And good use of that little caret key. Of course, on Pear Deck, you can type or you can draw. If you'd rather draw with, a mouse, or if you have a touch screen with a stylus or your finger. And remember that on exponentials, the decrease that's happening has to be based off of multiplication. In other words, we never subtract the values in our table because this is an exponential situation. You can't subtract the same value to create this table every time. So it's going to have to be multiplication. And since those heights are decreasing, make sure you are multiplying by a rebound ratio that is less than 1. If your rebound ratio is greater than 1, your ball will be increasing in height. Which means it will eventually end up leaving the Earth's atmosphere if it continues increasing in height forever. Imagine all the balls that have ever been bounced are like now in outer space because they just kept bouncing and bouncing higher and higher. Now that doesn't sound reasonable. Okay, looks like we need a couple more minutes. Okay, so like I said, you actually need to figure out the value B first before you can figure out the y-intercept, the drop height up here at the top. And what we know about B is the number that you multiply this by to get this. And then you multiply this by B to get that. So in other words, to work down the table, I need to multiply by B. So to get from 84.5 to 67.6, I need to multiply by B. I just need to figure out what that is. Is it what? 0. What? 8. Perfect. It is 0.8. Reason is because since that times B is that, we can figure it out by dividing. So notice 84.5 times B equals 67.6. How do we solve for B? We divide. So B is going to be 67.6 divided by 84.5, which is 0.8. That is B. Okay, B has to be less than 1. Otherwise, you would see increasing numbers here. So my B is 0.8. So that means to go down the table, I just multiply things by 0.8. So I take that number, multiply by 0.8, I get that. Multiply that by 0.8, I get that. If I want to work backwards up the table, I would do the opposite, which is divide by 0.8. Okay, so if I want to work back up the table, I can divide by 0.8. So now that I know how the table is being generated, to work down the table, I multiply by 0.8. To work up the table, I divide by 0.8. So I'll take the last number here, 84.5, and let's divide by 0.8. So the next entry on the table is 105.625. And then we got to do it one more time. Okay, so I get 132.03125. I'll just round that to 132. So we started the ball drop at 132 centimeters. And then we multiplied by 0.8 and then multiplied by 0.8, 0.8, 0.8. So to work backwards, you divide by B. To work down the table, you multiply by B. So I now know this value right here is A. So A is about 132. So I can now write the equation. So the questions that it was asking here, whoops, did not mean to do that. Let's go back. So what was the rebound ratio? Rebound ratio is 0.8. Okay. So in other words, it rebounds back up 80% of where it started, which is a decrease of 20%, by the way. It says, what's the rebound ratio right there? What height did he drop it from? He dropped it from 132 centimeters. So our equation is y equals 132 times 0.8 raised to x. There's the equation that represents the table of data for our bouncing ball. Okay, our next slide says a major technology company called ExpoGrow is growing incredibly fast. The latest prospectus, which is a report on the company, said so far the number of employees, which we're going to call Y, can be modeled with the equation Y equals 3 times 4 to the X, where X represents the number of years since the company was founded. How many people founded the company? That means how many employees did they have at the very beginning? And how can you describe the growth? Now, table, you don't need to draw a table, but we do have our X and our Y. It does say Y is the number of employees. And X is the number of years since the company was founded. So when X is 0, that would be the number of employees that founded the company. Founded means started. So how many employees did they have when they started the company? When X is 1, that would represent 1 year later. So like on the first year anniversary of the company, this value here would be how many employees they had at that time. Oh, swallowed wrong. So y equals 3 times 4 to the x is our equation. Sorry. So it says, figure out how many people founded the company. That would be the number that goes right here. And describe how the company is growing. It is growing. So the number of employees is increasing. How is it increasing? Okay, notice that it's an exponential equation. So that means it's increasing by multiplying by something. Exponentials increase and decrease by multiplication factor. Okay, so don't say that they add employees each year. They're not adding employees, they're multiplying their employees by something. Okay, so I'll let you guys work on that one. And By the way, you can answer this without completing the table. The table is cool, and I see a lot of you guys doing the table, and that's awesome. But the table is just one extra representation of what's going on. There are three representations here: the situation, the company itself, the table, and the equation. The only representation that we don't have is a graph. Because there's always four representations. There's an equation, there's a table, there's a graph, and you could create a situation. Good. So make sure when you describe the growth that you are talking about multiplying. The growth is multiplying. We know that because the equation is an exponential equation. X is in the exponent. A linear equation would be they're adding employees every year. Okay. Okay, so number of employees when the company was founded. Two ways to figure it out. One is to take this equation and change the x to a 0. The other is just to know, based on the equation, which number is the y-intercept. So if you look at this equation and you know, oh, that's the a value, that's the y-intercept, you can probably figure out that they started with 3 employees. But if you don't know that, notice that you can plug in a 0, because remember that 4 to the 0 power is 1. So this turns into 3 times 1, or 3. Okay? To figure out the growth, if you look at this equation and you realize that 4 is the growth, that 4 means we are multiplying by 4. So year 1, they're going to have 12 employees. Year 2, they're going to have 48 employees. If you didn't know that, plug in a 1 and see what happens. So y equals 3 times 4 to the 1. 4 to the 1 is 4. So you end up with 3 times 4, which is 12. And you can do that for x equals 2. And you should be able to see that, yes, we are multiplying by 4. So the answer to this question is there were 3 founding members. Those are the original employees. and the number of employees, okay, is increasing. It's increasing by multiplying by 4. So you can say something, the number of employees multiplies by 4 each year. Or here's a fancy word, quadruples each year. Quadruples is just a fancy word for multiplies by 4. But you can say multiplies by 4, that's fine. So the number of employees multiplies by 4 each year or quadruples each year. So if they keep going, they're going to end up with a very large company very soon. So it's not going to be able to continue much longer, but at least for these first years, the number of employees has been quadrupling. However, take a look at the next slide. As part of a major scandal, now this is scandalous, guys, it was discovered several statements in the Expo Grow prospectus were false. The company actually had 5 founders and doubles in size each year. So it's not quadrupling, it's only doubling in size each year. So what is the correct equation? So in other words, all of that is wrong. We had wrong information. So instead, we have 5 founders and it doubles each year. Yeah, so we're going to rewrite our equation. Okay, if you want to write a table, you can, but you hopefully can just go straight to writing the equation from that. Okay, remember your equation needs to start with a y equals. Some of you guys are not writing y equals, you're just writing the stuff on the right side of the equal sign. An equation has an equal sign. So it is connecting x and y. So make sure your equation has an x and a y in it. Okay, I am seeing good equations. Some of them are missing the y. Good. Okay, make sure your equations are exponential. Okay, so it looks like we did a good job there. 5 founding employees, that's the y-intercept. That's how many employees they had at year 0, at the very beginning. So that's the A value that goes in front. And if you are doubling each year, that means you are multiplying by 2. So very quickly, that should be the equation. So that's the starting value, number of employees, the founders of the company, and it doubles each year. Okay, and if you want to draw a table to go with it, you are welcome to do that, but it is not required because you can answer the question coming up with the equation just from this information right here. Okay, our next slide. We have a computer virus. It's affecting the technology center in such a way that each day a certain portion of virus-free computers is infected. The number of virus-free computers is recorded in the table at right. So we've got this lovely table here. And this is the number of days since the virus hit. We'll call that X. And then over here, we have the number of uninfected computers. So notice that at day 0, there were 27 good computers in the technology center. One day after the virus hit, there were only 18 usable computers. So 18 computers that were unaffected by the virus. You don't want to use a computer that has a virus in it. By day 2, there were only 12 computers left that were uninfected. Okay, so based off of that table, we have a few questions. The first one, how many computers are there in the technology center? And what portion, so what fraction or what percent of the computers are being infected each day? And how many computers will be virus-free at the end of the 3rd day? So the end of the 3rd day, that part is figure out the next value in your table here. So at the end of the 3rd day, how many virus-free computers will there be? And then the other questions are, how many computers are actually in the technology center? And what portion, what fraction or percent of the computers are being infected each day? Okay, so I'll give you a little bit to work on that. Yeah, making sure I keep an eye on the clock. We're doing good. Now notice that the values in that table are decreasing. So you need to have a B that is less than 1. If your B value is greater than 1, then you will have an increasing table. Bless you. So I'm seeing some 1.5 values for B. 1.5 would say that our table is increasing, and it is not. The virus is increasing, but the number of computers that can be used is decreasing, because as the virus, spreads, the number of computers that can be used in the technology center is decreasing. So we're actually counting the number of computers. We're not measuring the virus in this table. We're measuring how many uninfected computers there are. Okay, and this is all exponential. So make sure that your equation follows the exponential model. Y equals A times B raised to the X. Yeah. It's what? Yes. So what is it multiplying by? Remember, our B value is what are we multiplying by? So Devin just said the 1.5 that a lot of you guys are getting is that it's dividing by 1.5. And he's absolutely right. It is dividing by 1.5. But the question is, what is it multiplying by? Because our B value is what do you multiply by? So to figure out what B is, we got to figure out right here, well, what do we multiply by to get from 27 to 18? Or any of the values. It doesn't have to be the 27 and the 18. It can be the 18 and the 12. But what do you multiply by? Because even when your table is being created by division, there's still multiplication. Anytime you divide by something, you actually are multiplying by something. Just like whenever you add something, you're really just subtracting a negative. So whenever you divide by something, you can multiply by the reciprocal. Reciprocals are opposites in multiplication and division. So yes, I do understand why a lot of you guys are getting 1.5, but that is not the value of B. It's close. Oops, I did not mean to go to the next slide. Okay. So if you've got a 1.5 in your equation, you got to figure out how to fix it. Okay, so it looks like everybody's good with A being 27. So A, on day 0, before the virus has infected anything, there were 27 uninfected computers. So there are 27 computers in the technology center. So everyone was good with A being 27. The problem we're having is with B. Okay, B is what do you multiply 27 by to get 18? So 27 times B has to equal 18. So to solve for B, we need to divide by 27. So B is going to be 18 divided by 27. That is a fraction. You can divide both of these by 9, because 18 divides by 9, 27 divides by 9, which will give me a fraction of 2/3. So 2/3 is the value of B. If you divided it on your calculator, you probably got a decimal. The decimal would be 0.666 repeating. So if you want to put it in decimal form, that's fine. That's what 2/3 is as a decimal. It's a 0.6 with a repeating 6. So 0.66666, etc. But this is the value B. Now the 1.5, you guys are getting 1.5 because 1.5 is what you get when you flip this fraction over. If you flip it over and do 3 divided by 2, that's where you guys were getting the 1.5. So in other words, you were dividing these backwards. If you divide 27 by 18, you do get 1.5. So yeah, we are dividing by 1.5 as we go down, but we are multiplying by 2/3. So if you know what you're dividing by, all you got to do is flip it. And if you remember, if you want to know how to flip something, this is the key on your calculator that will flip something. So if you thought, well, dividing by 1.5, I wonder what my multiplier is. Flip it. 1.5 flipped over is 2/3, 0.66666, repeating. Okay, so there's our value B. So 27 computers to start with. So there are 27 computers. Okay. Now the second question is a little tricky. My value B is 2/3. That means start with 27. The next day, 2/3 of our computers are still good. The next day, 2/3 of those are still good. But the question isn't asking how many of the computers are remaining unaffected. The question is asking how many are getting infected. So if 2/3 of them are remaining uninfected, how many are actually getting infected? So if 2/3 remain good, how many are getting infected? 1/3. That was just a tricky question because the question was actually asking how many the virus is infecting. So 1/3 of them are infected each day. Okay, so that's what's going on. There are 27 computers in the computer lab. 1/3 of them are getting infected, which leaves 2/3 uninfected computers. And then the last question here is how many computers will be uninfected, virus-free on day 3? So 2 ways that I can do this. I can create the equation, which I never asked for the equation, but if you want to write the equation, it would be this. Of course, instead of 2/3, you can put 0.6666 in there. It's the same thing. And you can put in a 3 into your equation using your calculator. So 27 times 2/3 raised to the third. Or I can just take 2/3 and multiply it by the 12, because I know that's my multiplier. So 2/3 of 12, 1/3 of 12 is 4, so 2/3 of 12 is 8. So the next value on the table should be 8. So there will be 8 virus-free computers on day 3. Should say at the end of day 3, because it's measuring at the end of each day, I think. But anyway, there will be 8 virus-free computers on day 3. Okay, so that takes us to our last slide. Which is write an exponential equation that matches the table. Your Delta math tonight, this is what it's going to have you do. Write exponential equations from a table. And the table will have some ugly numbers in it, decimals and stuff. But with use of a calculator, you should still be able to figure out what the equation is. So there is the table. And remember that the equation should be written like this. Okay, so from the table, you need to figure out the value of A and the value of B. A is the y-intercept. Always when x is 0, that's what a y-intercept is. B is the growth factor or the decay factor. B is greater than 1 when the values in the table increase. B will be less than 1 when the values in the table decrease. So make sure that your value B makes sense. For example, this table increases. Look at those Y's. They are increasing. So your B better be bigger than 1. If it's not, you probably divided backwards. The easiest mistake to make is to divide backwards, but if you have an idea of what kind of value of B makes sense, it's easy to fix. So it's good to always have an idea of B before you calculate it. So even though I can't figure it out in my head, I do know that it's going to be greater than 1. Okay, good. And this is a fast one. A lot of you guys already have the answer in there, so that's awesome. Oh, wait. Only 4 of you have not, so let's wait a moment. Hey guys, I just adjusted the Pear Deck so that you can go back to other slides if you need to, since this is the last slide. I was keeping you on the problem that I am on purpose. But now that we're on the last one, if you do need to go back, you can. But on this one, okay, A, again, is the y-intercept. So go to your table, find where x is 0. that value right there is A. So this value is A. So I know that A is 1.2. B is the number that is being multiplied to create your table. So take any two numbers in your table. Now I'm going to take the two smallest ones. So right here, I know that I multiply by B. So 1.2 times B will equal 3.96. Which means I can find B by dividing by 1.2. So if you take 3.96 and divide by 1.2, you get 3.3. And we knew that B had to be greater than 1, so that's a number that is reasonable. If you divide it backwards, you would get the reciprocal of 3.3. And remember that on your calculator, you could quickly find a reciprocal by hitting that x to the negative 1 key. So if you thought that B was that, then it means you divided backwards. So if you got 0.30303030, etc., you divided backwards. And if you think you divided backwards, you can fix it easily on a calculator by hitting the reciprocal key. That's the B value, 3.3. Had to be bigger than 1 because we are increasing. So the equation, if you put this together, is 1.2 multiplied by 3.3 raised to the power. Okay, so again, that's what you're going to be doing on your Delta Math tonight, is looking at a table of values, a small table like this, and figure out what the equation is of the exponential. Okay, now not tonight, but to kind of think future-wise, what would happen if I gave you this table right here, but that number was missing? So suppose I had just given you these two values instead. Could we still figure out what B is? Yeah, it's a little bit harder, but that's where we're going. Okay, so tonight you will have all the values in the table that you need to find B, but where we are going next is, well, what if there's a missing value or values? In other words, what if you've got a value up here and then we skip some stuff and then there's another value down here? How can we still figure out what B is, because that's what we need, even if we don't have all the values in between? Okay, so you won't see that tonight. Tonight it'll be just like the one that is there on the screen, but just to kind of get you thinking, that's where we're going to go is, well, how do we find the value of B when there's values in the table that are missing? Okay, if you need to go back into the different slides, like I said, it is now on student paced, so you can go back and update or finish any of the slides that you did not finish. And it will self-submit. So when I end the session at the end of class, it will be, everything will be submitted, so you don't have to worry about submitting. If you are done with all of the slides, you can work on Delta Math. We got about 10 minutes, okay? So you might be able to get the Delta Math done. And then we are good. And then I will email the announcements to you guys. Okay, I'm gonna